Welcome back. In this lesson, we'll talk about hard and soft ferromagnet. So what do we define as a hard and soft ferromagnet? A soft ferromagnet is very easy to magnetize. As we discussed earlier, a soft ferromagnet, if you put a magnetic field, it will immediately magnetize it. And then as soon as you turn off the magnetic field, the system will become random again. So it's a soft ferromagnet, it's easy to magnetize, and it's essentially a temporary magnet, and has a low hysteresis loss, and then has a high susceptibility, permittivity, and then low magnetic energy storage. So what is so good about soft ferromagnet? Soft ferromagnet is actually extremely useful material in the sense that you can use it to produce electricity. And this is typically used because soft ferromagnet is so much respond to an external magnetic field. That means you can magnetize and demagnetize it very easily. But soft ferromagnet are very bad if you try to storage magnetic energy or you try to use it as a permanent magnet to try to magnetize system. Because as soon as you turn off the external magnetic field, the soft ferromagnet domains will start to form, and then there will be zero magnetization. So hard ferromagnet, is in contrast with soft ferromagnet, very hard to magnetize. And then it's essentially used as a permanent magnet. So that's why, for a north and south pole, you don't want to, use a soft ferromagnet. You want to use a hard ferromagnet. And then has a very large hysteresis loop, low susceptibility, permittivity, and then has a very high magnetic energy storage. So what is the key difference between a soft ferromagnet and a hard ferromagnet? So let's look at the hysteresis loop. And in the soft ferromagnet, your coercive force or coercivity region is actually very, very small. That means as soon as you turn on external magnetic field, you can very easily magnetize the system, and then you turn the field in the other direction. The hysteresis loop you see in the magnetization has a very, very narrow region. And this is the signature of a soft ferromagnet. In a strictly, completely soft ferromagnet, you essentially have no hysteresis region. That means the magnet will respond instantaneously to the external magnetic field direction. As soon as you turn off the external magnetic field, the system will completely relax to its domain world formation. You have some materials that actually behave like that. And in the case of a hard ferromagnet, you have very large region of coercive force or very large coercivity region. That means when you apply an external magnetic field, it takes a much larger field to actually magnetize the system. And then when you turn the field to the other direction, your hysteresis loop, as we have shown here, becomes much larger. So of course, this does not extend to infinity. Then you have really a permanent magnet. But in this case, the size, the amount of energy you can store in this system is actually determined by the region in which this reversible field actually occurs. And this is what we call is a hard ferromagnetic material, and this is what we call a soft ferromagnetic material. So let me give you a very simple example. Because in a lot of materials, you have an easy access of the system. So that means if you apply a magnetic field along the easy axis direction, obviously, it's going to be much easier to magnetize such a system. As we have shown here as an example of a monolayer of iron 001 on top of gallium arsenide 001. 001 means the reciprocal space lattice vector, and this is the one direction you can think about is along essentially the c-axis direction. And then you can see along the 110 direction of the field, it's very easily magnetized, as shown here. But along the 1-1 direction, it's very hard to magnetize the system. And then the difference is what we call the magnetization energy. And the magnetization energy essentially is defined as the amount of field multiplied by dm, the amount of field you change, and then you go through this loop. Essentially, how much energy you can store in the system is determined by the magnetization energy of the system. And of course, the differences will be the energy anisotropy you have. So what is the use of a soft ferromagnet? As I mentioned earlier, one of the very important use of a soft ferromagnet is to produce electricity. Another very good use of a soft ferromagnet is to have a magnetic shielding. That is to say, for example, in this sort of a picture, if you have an external magnetic field and you want to shield it, and you can use a soft ferromagnet, and then the amount of field inside the soft ferromagnet will be much less than the amount of field outside a soft ferromagnet. And the ratio of the two is what we call the shielding ratio, which is H out divided by H in. Of course, it depends on the size of the magnet you have in the system. So this is one of the applications you have for a soft ferromagnet. And the other thing for a soft ferromagnet is that you can have a very large electromagnet. That means your magnetic field will be generated when you apply a electric current, meaning you actually can spontaneously induce a very, very large magnetic field, and such a field can change direction very easily. And that's the nature of a simple soft ferromagnet. And the other application of a soft ferromagnet is, as we mentioned earlier, is to produce electricity. You can have a case in which the electric current can go back and forth, in which your magnetic field can go back and forth and back and forth. As we know, the electric current is produced by changing the mechanical motion of your magnet into a motion of the electrons, meaning essentially almost work the same way as diamagnetism, so that when your magnetic field is, or the magnet is changing back and forth in direction, in this case is rotating, and then you actually produce a current that tries to produce a field that counters to the rotational field direction of your magnet.